Dear students, today we are discussing about the integration, multivariable integration over general sets. Uh, Suppose that we are considering a region that is not necessarily in cell shaped, okay, and we have to integrate a function in that set, in that region. So in that situation, what can we do? So that will be discussed in this section. So let us consider f is a function from D to R, where D is a bounded region in Rn. So then there exists an n-dimensional cell Cn of AB, okay, in such a way that cell contains D. For example, I will show you. I will show you. For example, let us consider two-dimensional case. Let this may be the cell, okay, and let us consider a region, that is, let it be the region, okay. So what is this? This is the region D, and we are considering a function from D to R, okay, D to R. So at the same time, this square is actually a comma B, C2 a comma B, okay, C2 a comma B, and so we have to integrate the function. What is that? Yeah. We have to integrate the function over the region D. It can be a lamina, whatever it is. So in the for this D, for this domain D, we can select a cell C2a comma B in such a way that D is contained in the set C2ab. So that is the construction. So let us define a function, new function. What is that? G of x. So g of x will be f of x over the region D and 0 over the region D. What is that? Over the region outside the region D. Okay. So let us we have to define a function. We will define a function g. G is from, where is that? Yeah, G. Sorry. G is a function from Cn to Cnab to R. Okay, Cnab to C2ab to A to R. So this is integrable because we have defined the it is a definition of integration of function over the cell. So this is integrable. So you have to integrate f from D to R, whereas D is contained in C2a comma B. Okay, look at this construction. Okay, so what will be the integral over Cn of AB f of x dx? So that is exactly, that will be, what will be that? Yeah, we can construct that integration. I will show you. Here we can see that integral over df of x dx. So I will show you how you obtain that step. Okay, let us insert a function. Okay, that is integral over C n of a comma b, C n of a comma b, g of x dx. These are all vectors. Okay, this multivariable integration. Think about multivariable integration only. Okay, So this can be written as, we know that what is g of x? G of x is equal to f of x for x belongs to D and 0 for x not belongs to D. So we can divide the entire region Cn a comma b into two equal parts. In what are the two regions as a union of two sets, and one set is D itself. Okay, one set is D and other set is C2AB minus D. That means D complement intersection C2AB. So we can separate into two integration. What is that? One is D. In D we know that this is nothing but f of x dx plus, and the second integral is, what is that? Yeah, the D complement intersection or we can say like this, C a comma b difference D. Okay, what are the notation we are using? You think about that, you think about the blue region. Okay, that is, you can use any notation, what will be that. Okay, so here it is 0, so dx, so this is a step. So we know that this is 0 exactly, and this is nothing but integral over d f of x dx. So that is obtained here. So you know that here there is no Cn of a comma b. So this right side integration is independent of the selection Cn a comma b. Okay. So that is and now we define one term, that is Jordan content or characteristic function. Okay, let D subset of Rn be a bounded set such that D subset of Cn a comma b for some n dimensional cell. Let the function lambda d from Rn to R be defined as, it is an indicator function, or it is known as characteristic function of D. It is an indicator function. Usually it is known as characteristic function of D. So what is the structure of a characteristic function? Do you know what is the characteristic function? Yeah, let it be y-axis and let it be x-axis, and let us take a set D. D is the region from D is a region from, where is it? Yeah, okay, let us consider this is the region of D. Okay, this is the region of D. So what is characteristic function? Let us define let it be 1, 2, 3, etc. 1, 2, 3. So what will be the characteristic function? Yeah, over region D the characteristic function value is 1. So what is the integral value? Integral will be area under the curve. Okay, so it is 1 for x belongs to D and it is 0 for x not belongs to D. So in all other parts we know that it is 0. So there is only positive number 1 Okay, in all other regions it is 0. So this is let us shade this part. Okay, you can put a color. So this will be the integral value, area under this curve. Okay, so I want to show you that the lower sum and upper sum over this region. I want to show that the lower sum of this function and upper sum of this function in this region is same. So infimum of upper sum equal to supremum of lower sum. So that means we can say this equation, supremum of LSP lambda d equal to infimum of USP lambda d. Okay, lower sum and partition corresponding to any partition. Whatever be the partition, the lower sum and upper sum will be same. We can for example, we can partition like this. So let this be the sorry. This be a partition. What is the lower sum? This partition lower sum is same as upper sum. Okay, in this case lower sum is same as upper sum. Okay, so whatever be the partition we are taking, the lower sum will be equal to upper sum. So the infimum of upper sum will be same as supremum of lower sum. So this what is that? Then D is said to have n-dimensional Jordan content denoted by mu jd, where mu jd is equal to the common value of the terms of inequality 7.6.6. So that is known as Jordan content. Okay, so this common value, this area is usually called Jordan content. Okay, this common value is equal value, common value is known as Jordan content. So in this case D is said to be Jordan measurable if it is possible, if it is equal, or so in this case we can say that D is Jordan measurable. So just think about the Jordan content and Jordan measurability. There are two theorems. You can consider the what is that, a term boundary. Okay, what is boundary? The boundary term is defined in this section. Have you studied that term, boundary of T? I think we have discussed in the beginning class boundary of the function, boundary point. In that case we will have only two dots, 2 points. In the case of this Jordan content, we will have only 2 points for as a boundary. So in that case we will have Jordan content equal to 0, because for a single point, what is the Jordan content? Yeah, the area under the curve from A to A. What will be the area under the curve? That will be 0. And in the case of second point B, the Jordan content will be 0 for the boundary points. Okay, so that is the theorem. So we are not proving all these theorems. Let's just remain only. Okay. Similarly, we can have another theorem, f from D to R, where D subset is bounded and Jordan measurable. And if f is bounded and continuous in D except on a set that has Jordan content equal to 0, then integral d f of x dx exists. So we are not discussing the proof of this theorem. Okay, we are just reviewing only. So let us look at the example, then you will get more ideas. Let us consider f of x1 comma x2 equal to x1 into x2. Okay, so D be the region such that a circle less than or equal to 1. So what will be the region? Yeah, circle with origin 0, 0 and radius 1. Okay, x1 square plus y1 x2 square less than or equal to 1. So, and moreover we have given that x1 greater than 0 and x2 greater than 0. So it is a positive quadrant, the positive quadrant part of the circle. Okay. So I will show you the shape of the domain. Let us look at the shape of the domain. Yeah, it will be a circle, but not full circle because it is divided into 4 parts, and we are considering only this region. Okay, we are considering only this region. So this region only. So that is this region. So it is easy to see that D is contained inside a two-dimensional cell. Yeah, it is clear that we can see that you can draw a rectangle in such a way that this region contained in that rectangle. Okay, this is a rectangle and the region is contained in that rectangle. Okay, so that is C2, that is denoted as C2 0, 1, and that region is contained, that integration, the integration in that region can be solved by using these steps. Okay, we can consider what is that, a lamina from 0 to x2. I will show you that. You can consider a lamina range of this lamina is 0 to x2. What is x2 exactly? x2 equal to, since x1 square plus x2 square equal to 1, since this boundary point is exactly equal to, what is that, x1 square plus x2 square is equal to 1, then x2 will be 1 minus x1 square, x2 square will be 1 minus x1 square, so x2 will be root of 1 minus x1 square. So this can be considered a lamina that integrated from 0 to root of 1 minus x1 square, and then move this lamina to from here to up to, what is the movement region, up to 1. So 0 to 1 we can move this lamina from 0 to 1, so we will get the area of this region. So that is the procedure, region of that integration. Okay, so this is the step involved in computation of integration into 0 to 1 minus x1 square root 2 x1 x2 dx2, and x1 is moved from 0 to 1. Okay, so that can be solved like this. Okay, that can be done by you, no problem, it is possible. X1 can take it outside, just integrate with respect to x2 only. The result is nothing but 1 minus x1 square into x1, 1 by 2 is there, dx1. Okay, whatever is this simple integration, we get 1 by h. So this is the area. Okay, so we can integrate f over that region, over this region, over this red region. Okay, so that is the methodology. So we could integrate over this region using this lamina property. Okay, so we obtained this result. You can read this. So another example is, consider double integral d e raised to x square dx and dx, where d is the region in the first quadrant bounded by x2 equal to 1 and x1 equal to x2. So what is the region? Let us consider that region. This equal 1. What is x2 equal 1? x2 equal 1 means x2 equal 1 means, yeah, this is x2 equal 1. Okay, x2 equal 1. Okay, now another region is x1 equal to x2. What is x1 equal to x2? 45 degree line. 45 degree line. This is x1 equal to x2. So which is the area bounded by this region? And moreover we have, it is first quadrant. So it is in the region is nothing but this one. Okay, this is the region. So again we can consider to what is that? Again we can consider a strip here. Strip start from 0 and end at x2, x1 equal x2. So x1 start from 0 and end at x2. And again we can move this strip from 0 to 1. Okay, move this strip from 0 to 1. So we can cover this region. Okay, so integration can be done using that step. So double integral over d e raised to x2 square dx1 dx2 equal to integral of 0 to 1. Integral 0 to x2 e raised to x2 square dx1 into dx2. You can simplify like this. Okay. So again one more example is there. You can done in your notebook, or you may try yourself. Okay, I have done 2 examples. You can try these examples in yourself. So these are the integration techniques for the general region. So we will cover the inner region in cells and we will integrate like this. So that is the idea. Now we may consider change of variable in n-dimensional Lyman integrals. I think we might have studied change of integration in univariate case. If phi is equal to some x square, if phi equal to some ax plus b, so we can integrate the function with the change of variable case. Okay, so let us consider the similar problem in the multivariate case. Suppose D is the closed boundary set in Rn, and let f from D to R be continuous. And suppose that h from D to Rn is a one-to-one function with a continuous first order partial derivatives such that Jacobian of determinant of jh of x. Then we have studied. Okay, we have already studied. Such that determinant of jh of x equal to dou h1 h2 extra hn divided by dou x1 dou x2 extra xn is not equal to 0 for all x in D, where x belongs x equal to x1 x2 extra xn prime, and hi is the ith element of h. Then the theorem states that integral over d f of x dx equal to integral over d dash f of gu into determinant of jg of u determinant of du, where d dash equal to h of d and u equal to h of x, and g is the inverse function of h, and determinant of jgu equal to dou g1 g2 extra gn by dou u1 u2 extra un, where gi and ui are respectively the ith terms of g and u. Okay, so this is very much useful in statistics, because sometimes we have to find out the distribution of, or the area or probability of change of variable case. Okay, so in that case we can use this theorem. So similar, there are several situations change of variable occurs in statistics. So in that statistical theory we can use this theorem. Okay, the technique is based on Jacobian transformation. So the proof is not given here. At the same time we can discuss the problem. So this is very much useful in statistics. So what is the conditions? H is a one-to-one function with continuous first order partial derivatives. Okay, such that Jacobian determinant determinant of J h of x equal dou h1 h2 x hn by dou x1 x2 xn is not equal to 0. What is meant by determinant not equal to 0? It is invertible. Okay, the Jacobian is invertible or non-singular. So that are the matrix properties of a matrix properties of this matrix J h of x. Okay, so this determinant not equal to 0 means this is invertible. Okay, H is invertible. Moreover, it is non-singular. So we can apply matrix theory results in the integration theory. X is as usual the vector and hi is the ith element. So integral over d f of x dx is same as integral over d dash f of g of u. Okay, f of g of u, where g is exactly, what is that? You know, u is equal to h of x. U is equal to h of x. Then x equal to h inverse of u. Okay, x equal to h inverse of u. So g is the inverse function of h. That means h inverse of u means g of u. Okay, so g is the inverse function of u. So f of g of u into determinant of j g of u du. So that is as usual multivariate integration. So this is possible when determinant of both the determinant of j h of x and j g of x are existing. Okay, and you know that the determinant of j g of x, j g of u is equal to dou g1 g2 etc gn by dou u1 u2 etc un. Okay, so this is possible. What is the minimum requirement? Yeah, it should be one-to-one function with continuous first order partial derivatives, and this Jacobian determinant is a non-singular or what is that invertible. So in that case we can find out the what is that integral value of f of x using change of variable, transformation of the variable. So this is more useful in statistics. I have already told you this is very important in statistics. So let us look at the example. Consider the integral double integral over d x1 x2 square dx1 dx2, where d is bounded by the four parabolas. What are the region? X2 square equal to x1, x2 square equal to 3x1, x1 square equal to x2, x1 square equal to 4x2. You think you can draw the four parabolas and you can think about the common region. Let u1 equal to x2 square by x1. That is that u1 equal to x2 square by x1 and u2 equal to x1 square by x2. Okay, that is that u1 equal to, the transformation is nothing but u1 equal to x2 square by x1 and u2 equal to x1 square by x2. So what is x1 in terms of u1 and u2? Yeah, x1 in terms of u1 and u2 can be written as, what is that? Using these equations we can write, let us just multiply this u1 with the u2 square and take the cube root. Okay, so we will get, so from using this u1 and u2 we can find out that x1 equal to u1 u2 square raised to 1 by 3. Similarly x2 equal to u1 square into u2 raised to 1 by 3. Okay, so we can differentiate with respect to u1 and u2. Okay, we can differentiate with respect to u1 and u2. What is that? Dou x1 by dou u1 and dou x1. So you can apply this, what is that, Jacobian formula. Okay, determinant, and we will get it as, you have to try for this, for getting this minus 1 by 3. you may do in your notebook. You can find out that dou x1 by dou u1 and dou x1 by dou u2 as the first row, and second row dou x2 by dou u1, dou x2 by dou u2 in the second row. Take the determinant of that. Okay, so you will get like this. What is that? Dou g1 g2 etc gn by dou u1 u2 extra u1. Instead of we are getting dou g1 by g2 by dou u1 u2 equal to minus 1 by 3. You may check that. Okay, so we can apply the formula. What is the formula? Yeah, this is the formula 7.67. What is that? Integral over d dash, integral over d dash, integral over d x1 x2 square dx1 dx2 is same as integral over double integral over d dash. You can write this f in terms of u. Okay. So what is that? u1 x1 is actually u1 u2 square raised to 1 by 3. Substitute that. Again x2 is x2 square is u1 u2 u1 square u2 raised to 2 by 3. So you can substitute and simplify like this. You will get this step du1 du2. So you can what is that? You will get the you will get the integral like this. Okay, you can see that d dash is the region in u1 u2 space bounded the lines u1 equal to 1 comma 3 and u2 equal to 1 comma 4. So think about that region. Okay, what is the range of that integration? What is the range of u1? Okay, what is u1? u1 is exactly x2 square by x1. So you can see that that is the region of the maximum values, or what is that? Maximum value that can be possible is 1 comma 3. Okay, region bounded by the lines u1 comma 3 and u2 equal to 1 comma 4. So in that case we can see that integration is possible. 1 by 3 into integral 1 into 3 u1 square u1 raised to 5 by 3 du1 and integral 1 4 u2 raised to 4 by 3 du2. So substitute and you are getting the result like this. Okay, so you can construct that, you can derive this, or you can simplify this problem, and you may try to get this answer. Okay, so I think this is sufficient for today's class. You may write these results and solve these problems.